Okay, well, again, I'm Ken Tate, and I see a lot of familiar faces out there. Welcome to all of you, and to folks that I'm meeting for the first time as well. We're glad you came. And normally Rob Atwell, our companion from the vet school, would be giving this portion of the talk, but unfortunately he wasn't able to make it today. Had an unexpected emergency come up, so I get to give his talk, and it'll have much less of a veterinary scope than not, because I'm not a veterinarian. I'd like to pretend I am, because they're pretty cool, but I'm going to have to stick to being a hydrologist, so there'll be a lot more in-stream stuff. And as Randy indicated, one of the things that we're consistently seeing across the state on rangelands and irrigated pasture relative to water quality are issues with, figure this thing out, microbial pollutants of concern. Things like Cryptosporidium parvum, potentially salmonella, and the one that we see an awful lot of is E. coli. And so what I'd like to do today to start with, and hopefully this will go away in a minute, I'm afraid to touch any other buttons, is give you a bit of an overview of the pathogens and indicator bacteria that would logically be of concern in systems like this where we do have production livestock systems in these watersheds. Talk about indicator bacteria dynamics and runoff. Basically, what do we see at multiple spatial scales at the end of the field, at a small watershed scale, and then all the way down in the delta relative to these constituents? What kind of numbers do we see? What types of seasonality? And then finally talk about the correlations that we're seeing or not seeing between indicator bacteria, which we regulate on and have standards for, and pathogens of concern, the things that we're worried about that'll actually cause infection, cause illness. And so, concerns about outbreaks, infectious disease outbreaks from drinking water and recreational activities such as swimming, boating, those types of things, have been driving the concerns about microbial pollutants and water quality for a long time. And this is just a snapshot of the outbreaks that we've had for the types of organisms, protozoa, so kind of an egg shape like Giardia, Crypto, and these have been around a long time. They do not replicate outside of the gut. They replicate in the gut and then they're dormant in the environment until they're ingested, so they're very commonly a fecal-oral type of transmission, as well as bacteria. And so from the protozoa, Giardia, which has been around a long time, over this time period in the U.S., 27 confirmed outbreaks, 18 attributed to drinking water, 19 attributed to recreation. Cryptosporidium, similar types of numbers. And Cryptosporidium parvum really rose to the forefront in terms of notoriety. Some of you might remember in the early 90s in Milwaukee there was an outbreak. About 100,000 people got sick in the city of Milwaukee. They traced it back to the drinking water, and I think there were over 100 deaths. And this really brought Cryptosporidium to the forefront for CDC, food safety issues, as well as EPA and others. And here in California, we've been, my entire career now for about 15 years here, we've been studying and chasing Cryptosporidium as the predominant waterborne pathogen of concern, particularly with relation to livestock. But not to ignore some of these other, particularly the bacteria, E. coli 0157, there's been a significant number of outbreaks, and then fewer with Campylobacter and Salmonella, which are more commonly related to food products, but can be found in water as well. And so, the gorilla in the room in the last several years in California has been the recent outbreak of pathogenic E. coli linked to spinach in the Salinas Valley in the San Benito County area. And basically there's, I won't imply that there's a connection between livestock and the rangelands that surround these leafy production areas, but without a doubt the close proximity. I think the only thing keeping that cow out is that gate. Sure hope the guy remembers to close it, right? So there is proximity, and there is a real reason to evaluate whether livestock are a part of this outbreak problem. And there's the impression that we have had that one outbreak and that's what's driving our concerns. The reality is there's been over a decade, now plus a decade, of food safety issues related to uncooked greens traced back to California. So this has been a chronic problem. It's just finally really come to the forefront. CDC and others have basically said enough, and there's an awful lot of effort going into the Salinas Valley and other places right now basically to try and rectify this problem. and consistently E. coli and to some extent Salmonella associated with these outbreaks. Now these are just the ones we know about. It's really difficult, particularly in the past, to capture for the medical community and the human safety community locally or nationally to figure out, hey, we just had an epidemic. We just had something really bad move through our population. Because 10 or 20 people get sick, they go to the doctor's office, they don't all go to the same doctor, and pretty soon, 2 or 3 weeks after the fact, the medical community starts to figure out we've had something pass through. What we're seeing now is the minute somebody comes in with gastroenteritis, there's evaluations of whether or not they've been infected with some of these pollutants, and we're seeing a higher incidence, reported incidence of foodborne human health illness issues. And so thinking about livestock, and primarily thinking about beef cattle production systems and sheep production systems, what we have primarily in California on our rangelands and irrigated pasture, primarily cattle. We can look pretty exclusively, for the time being, because we've got our hands full with these, looking at the protozoa, which would be Cryptosporidium parvum and Giardia. And basically, protozoa are what we'd call hard to eliminate. Basically, you can take the oocyst, the eggs, maybe you can rescue me from that thing. You can take the egg of Cryptosporidium parvum, take Clorox off the bleach in the grocery store, put those eggs in it, into that Clorox, let it set for a couple weeks, take it out, feed it, and it'll infect. So we have a really hard time chlorinating it out. So that's why there's so much concern about it. There are ways to ramp up the water treatment facilities so that we can filter it out. But it's 5 microns in size. It has a negative surface charge, a slightly gram-negative charge. And so it passes right through most of our treatment systems quite well. Bacteria are relatively easy to eliminate. You know, we all shock the pool at home and kill all the bacteria, so we're okay. But if we shock the pool at home, we have not killed Giardia or Cryptosporidium parvum. And the ones that we worry about, again, in general, pathogenic E. coli that produce Shigatoxin 1 or 2 toxins, or a variant 0157, Salmonella and Campylobacter. And so, first off, I really, Rob Atwell, as an epidemiologist, will never say the word pathogen when he's talking about E. coli in general or fecal coliforms. They're very clear about talking about what an indicator bacteria is versus a pathogen. And so what an indicator bacteria is a bacteria that, when present in water, indicate the presence of fecal coliform or pathogens. So we're looking at these indicator bacteria, hoping they'll tell us what is the risk of human health, to human health. What is the risk that, 1, there's fecal contamination of the water, or 2, that there are some pathogens that might make us sick in that water at the same time we see indicator E. coli, or fecal coliform, or Enterococcus, which is often used more in saltwater systems. And so these are the common indicator bacteria, and for most of these you'll find somewhere in some state, in some regional board, a standard for these constituents, depending upon, and it varies greatly. Anywhere from the Enterococcus value for Hawaii, for swimming beaches, I think is 7. For E. coli, it's, for a grab sample here in California recommended by EPA, it's 235. So it's quite variable. What we hope is there's a strong correlation between these and these pathogens that, from a livestock perspective at least, we're interested in. And so, conceptually, ideally, you'd look at the concentration of, say, C. parvum, and we decide for C. parvum, if we get above 50 oocyst eggs per liter, we have a risk of people becoming sick. That's the concentration at which an unacceptable number of people will become infected. We go across then via the correlation that exists between C. parvum and generic E. coli or indicator E. coli, find out where those two meet, and a standard is born. That's the relationship that we hope exists. So I'll oversimplify this, I know, but just to reiterate, there's a lot of complexity in the standards that exist across California, depending upon the beneficial use, depending upon the regional board that exists. There are freshwater standards for E. coli and fecal coliform. The kind of the metric that I'm going to use now, because it's the only unifying metric that I can find across regional boards, is the EPA's current nationwide recommendation of a geometric mean of less than 126 bacteria per 100 ml for greater than 5 samples collected over a 30-day period. So the average of those hopefully is less than 126. If you just take a sample at a point in time, and I think this is probably true for the Irrigated Lands program here in the Central Valley, the standard that's applicable is 235. So those are numbers that we hope to be below. So just a little background on indicator bacteria. Primarily, the ones for fresh water are all one big happy family. There are the total coliform group, which is a huge group that we used to have standards for. Many of you might remember we did a lot of work on total coliforms, and then we started looking at fecal coliforms. Both total and fecal grow very well in the environment. Naturally, they'll grow in mulch, they'll grow in the soil. So this is a very poorly chosen name because it implies it's only from fecal material. That's absolutely not true. A type of fecal coliform is the broader group of E. coli, and trying to find a better term for this word, I've selected indicator E. coli. And so what we've done as an academic group and as a regulatory group over the years is we've moved from total to fecal to indicator E. coli as regulatory standards, knowing that the correlation between indicator E. coli and, say, Cryptosporidium parvum is much better than the correlation that exists between total coliforms and, say, Cryptosporidium parvum. So we've been honing in. If we take that a step further now and look inside of indicator E. coli, there's always a malcontent. E. coli is one of them. There's a subgroup within E. coli that are pathogenic, basically that produce Shiga toxin E. coli. One type of Shiga toxin producing E. coli, there are many of them, is the one we're most familiar with, 0157. And then if you look at, say, the recent outbreak, it's not so recent now, several years ago, out of the Salinas Valley, there's a very specific strain of 0157 that was responsible for that outbreak. And unfortunately, the one that was responsible for the last outbreak was extremely virulent and caused mortality. And so, back to cattle, which is what we all work on and are concerned about. Well, we look at the old cow with her calf, pretty standard range cow. Colors are a little funny, some of you might think, but that's the one I had. I didn't have a nice black baldy or a nice Harris Ranch Angus to show you, but if we look at fecal coliforms, if you look at what's in a cow, what's in a gram of cow feces on a wet weight, 10 million to 100 million are excreted per gram by that cow and her calf every day. All classes of animal, regardless of age or sex. If we look at indicator E. coli, it's about an order of magnitude less, about 1 million to 10 million per gram feces per day. So how much manure does a cow excrete? 20, 30 pounds a day, wet weight, maybe more. You start doing the math on that, and there's a lot of zeros. And so I can already tell you, if we put cattle in a landscape, and there's any hydrologic connection at all between the cow and the stream, we're going to see some E. coli increases in that water. There's just no way around it. Because there's such a high number in these animals, and they need to be in the gut, because the cow's rumen works in a symbiotic relationship and a helpful relationship with the bacteria that exist in her rumen. So we want cattle to have bacteria in their rumen so they can grow and reproduce. So if we start thinking about then, what is it we see? If we look at what's coming off the field, irrigated field here in the valley, what's coming off of a small watershed here in the annual rangeland, a couple hundred acres, maybe the scale at which we manage a field and make grazing decisions here in California and down here in this landscape, and at the larger watershed scale where primarily the watershed is range and wildland area. What kind of differences do we see in concentrations through time in the indicator bacteria, and then what are the ramifications of this monitoring and meeting water quality standards, similar to what Randy talked about. And so starting here at the field station on annual rangeland, again, Toby will talk much more about these watersheds we've been monitoring for quite some time, but we have watershed both here at Sierra as well as over on the coast at Hopland. And it looks like this kind of landscape, anywhere from 20 to 300 acres in size. Generates runoff primarily, hopefully, when we have rainfall and during that part of the season. And they're generally dry during the summer. And so from the Shubert Watershed. Randy kind of explained one of these. Boy, I tell you, this thing is a mess. He hit escape there and won't come unglued. Okay, that might be good. Yeah. All right, so if we look at stream flow from the Shubert Watershed, looking at a storm early in the year, another storm early in the year, just a couple days apart. So, here's noon, here's midnight, here's noon. This is just a couple of days, which are the kind of storms we get here that generate runoff. They move right through these frontal systems, things up, we get some runoff, and then we have a few sunny days, and then we get it again. And so the blue line is the storm response. The dots over here on this axis are E. coli, or the red, fecal coliform, or the yellow. And you can see the same as with many other constituents, sediment, nitrogen, phosphorus. We see an increase, very dramatic increase, and a reduction in both of these indicator bacteria over the course of just a few hours. And you look at the numbers here, we're talking 10,000, 2,000. So we're going from 1,000 up to 10,000 and back down. So an order of magnitude change. And so when you get out and do your sampling is going to have a lot to do with the level of this indicator bacteria that you find. And the question about what would be a good average. This is even worse than what's coming off of perhaps a farming field where things are a little more consistent. We're talking about an order of magnitude, so you might need hundreds and hundreds of samples to get a good average for what's coming off of one of these streams over the course of a given year. That's certainly what we've done to characterize these patterns. And it's hard to sustain, I have to say. It's a lot of work. Looking across the season, if we look at that in same watershed, the storms that we were looking at were right in here, these two storms. But if we take a step back, look from the first little rainfall event that occurred. This is probably in 2001, 2002. You can see we had really high levels early on as we had these very small storms, and then as the season progressed, even with bigger storms, we saw lower levels of E. coli. Part of that is a flushing of the E. coli that's available in the system, and part of it is this initial flush right here. This probably, with all this flow, was probably just mainly dominated by a little pickup of in-stream flow and what was in the channel itself. So most of this E. coli right here in this storm, and probably these storms, is what's in the sediments in the bottom of the stream. There's probably not a lot coming off the land at that point. The main point of this slide is to show a little data from Hopland. Toby's going to talk a lot more about here. But over there we have 4 oak woodland watersheds, A, B, C, and D. We're very original when we name our watersheds over there. Here we have Shubert, which they named before us, and I came and we named them 1, 2, 3, the remaining ones, so we wouldn't get confused with A, B, and C, so we know what field. But we have 2 watersheds over there, and these 4 watersheds are side by side. They're all along the same hill, the same type of vegetation. 2 of them have not been grazed by domestic livestock, by sheep, since 1955. 2 of them, at the time of this data collection, it's longer now, 2 of them are grazed by sheep as part of their lambing operation, so they get moderate to heavy grazing because they're a lambing field. Look at the concentration on average over the course of that year. Take 50, 60 samples per watershed over a year, take the average, and you see a couple of things. One, relative to this particular standard, and we're using the average here since these are a lot of samples, even without domestic livestock, there's still enough background. There's still enough deer, there's still enough environmental growth of E. coli in the grass and litter, so that we still have trouble meeting that standard on an average basis. Certainly some samples are below and some are over because this is a mean, but as Randy said, we may be teetering at having any degrees of freedom to comply with that standard on some of these landscapes. Without a doubt, if you add livestock into the mix, this watershed's most comparable. A is most comparable to C, B is most comparable to D because of size issues. These 2 are much larger than these 2, and you'll see that we definitely, as we would expect, see higher numbers when we have livestock. But if we ignore the management, you could see that in some cases you might indicate that there's potentially a lower level in the grazed than the ungrazed, particularly for fecal coliform. So the difference between moderate, light grazing and background is generally not that much. It's when you introduce heavy grazing that we start seeing them really split out. So, change systems a little bit. Now we're still at the field scale. What's coming off? It's right below the cow. That's what a lot of that was on annual rangelands. If we look now at irrigated pasture, what are we seeing? Valley flood irrigated pasture, the kinds of irrigated pastures that we have here in our oak woodland foothill landscape, we see that this is an irrigation event. We got tailwater runoff, so this is tailwater coming off a field over just a 7-8 hour event. So we get tailwater come up and come off. This is from our field station. We have some fields that generate a lot of tailwater because some of the water that comes off of one field goes on to another field as its irrigation source. So we run a lot of water off some of these fields, and we see fecal coliform, E. coli standards spike early in the irrigation event and then tail off very dramatically. So at the bottom of the field, from an irrigated pasture perspective, we'll still see from 20,000 to 80,000. Now remember those numbers off of annual rangeland? I was going up to about 10,000, right? An irrigated pasture, going up close to 80, 100,000 E. coli. The standard's irrelevant to that. Even 225. We're out here at 80,000 coming off some of these fields. If we look across, this is some data from a private ranch where they were very kind. They allowed us to come in over an irrigation season. They regularly irrigated from June through September. This is down in the valley floor. And we sampled their irrigation water, what was coming out of the pipe. And then we sampled, these are reversed, we sampled their tailwater. Their irrigation water is the black. This is wrong. The black is what was going on to the field in terms of concentration, and the white, the open, is what was coming off. And so this is what was going on, and this is what was coming off. And you can see that one irrigation was very low. You come back a couple weeks later for the next irrigation, and it jumps right up to high numbers. This is a function of grazing management. There were no cattle in the field at the time of this irrigation. The field was actively grazed at the time of this irrigation. So you can see a lot of variability, and it gives us a hint that management, we know, even though the numbers are high, we know that we can do something with management, essentially to lower these numbers. So back to the study Randy talked about, where we did this large survey, share a bit of that data. We take a step up in spatial scale now and look at watersheds that are 10,000 acres to maybe 50,000 acres in size that are primarily rangeland, a little bit irrigated pasture. What do we see at that next spatial scale up, where you have maybe multiple ranches integrated, generating runoff and contributing to water quality levels? And to look at that whole data set, Randy showed you the mean of the rainfall-driven sites, the mean of the rainfall snowmelt, and the mean of the snowmelt. So this is below a couple thousand feet, annual rangeland coast system. That's where these are. These are Sierra, front face of the Sierra, the west slope of the Sierra, where the watersheds extend up into the snow regime, so up to 6,000 to 7,000 feet. A lot of them are down in the South Sierra as opposed to the North Sierra. And then these are, up in the mountain meadow systems in the upper Feather River, on the east side of the Sierra Nevada, the upper Pit, those areas where most of their rainfall, most of their runoff is generated from snowmelt. We see that same pattern. But what I want to point out is within here, you see an immense amount of variation, watershed to watershed, in terms of the concentration of both fecal coliform and E. coli. And that's hinting at inherent watershed differences. It's also hinting at some management differences. And one of our students right now is working on doing some watershed scale analysis to try and understand why that one's different than that one, so that we can get some hint of how we can manage perhaps at a watershed scale, or what are the inherent traits of a watershed that would lead to high versus low levels. If we look at it over time, the seasonality, we look from the water year from October through September, put all of the annual rangeland watersheds together, and take their mean by month, and we see that flushing in October, that flushing in November, which is just as Randy describes, that's that mobilization of the in-stream sediment and the constituents attached to those. And then we see consistently, we see this, not just in the annual type, we'll see it up in the mountain as well, a bit of a spike in July, late June, early July, where I don't know if this is some irrigated pasture return, or just getting warm conditions and getting a lot of environmental growth of these bacteria out there in the near stream areas. But that's a consistent thing that we'll see during the summer. The Delta. So I fish in the Delta. I don't work there very much, but my colleague, Dr. Rob Atwell, both lives there and works there. And so he's got a study going in the Delta, has had it going for a couple of years now, basically looking at 88 sites that they monitor once a month for 2 years, across kind of the east and north part of the Delta, looking at indicator bacteria, as well as looking at these particular pathogens. And what Rob has found, I'll show you the sites. And so there's Rio Vista over in here. Funny, he lives in that area, so he makes it just as big as Sacramento or Stockton. That's Rob for you. But these are all his sites, you know. So there's, what was that? It's probably Frank's track, right? So Tracy all the way up around into the areas north. So really significant sampling. There definitely are livestock produced in this area. Here's some cows coming over a bank to take a drink out of a slough. The sampling was intended to be above and below these types of situations, above and below a water management facility such as a pump or a drain, to try and get some predictive capacity spatially and temporally. What do we see in terms of these constituents across the delta? And I won't go into a lot of depth because he's not here, and I certainly would get it wrong. But one of the things he did send me that I thought was very interesting to bring in was out of over almost 1,900 samples collected over these time periods for indicator E. coli. This is the frequency of the concentration. So 70% of the samples were less than 25. So even in the delta, kind of a soup from our perspective up here on the mountaintop, you know, where it's nice and clean, still 70% of the samples than 25. About 5% of the samples out of these 1,900 that were collected were in exceedance of 235. But asking about the question about what does it take to trigger a regulatory action, for the current irrigated lands program, as I understand it, it takes 2 exceedances at a spot. And so 5% of that many samples is more than enough to trigger a regulatory program. But looking at it this way, we might not be that concerned. So it really just depends upon the individual program and how somebody's looking at the data and their outlook is. For me, looking at the numbers that I see coming off irrigated pasture and rangeland up here, gosh, we'd love to have numbers that low up here. So then, to move right on into the crux of it. So we see indicator bacteria in high levels coming off of these landscapes that we manage and that we study consistently across the state. We see seasonality, we see some management patterns. But from my perspective, thinking about what is the human health risk that's associated with these high levels of indicator bacteria numbers, do these indicator bacteria equal the presence of pathogen in water? Is that correlation I talked about valid? And so, do we have something like this? Do we have a relationship that's nice and clean, we can shoot a line through and confidently predict from indicator bacteria what our pathogen numbers are? And so we've been conducting some studies to try and get at that. Some of the studies are actually at the end of the cow. Rob does those, thank goodness. I don't like working at the end of the cow, to be honest with you. I went to school for a lot of years not to work at the end of the cow. But he went even more years and still works at the end of the cow. If we look at, did a survey working with the livestock industry who's been involved in almost all of our research. If you look at the percent of animals infected, so out of 100 cows, or 100 cattle, how many are infected? We see a relationship for C. parvum in range cattle in California between age and months and the infection rate in the herd and the shedding rate in the feces. So found pretty clearly over thousands of cattle in California that calves about 4 months of age that aren't too old, they are 10 to 15% of the calves are infected with C. parvum and are shedding at about 100,000 oocysts per gram. Takes about 30 to 100 to make a person sick, and so that's a pretty good shedding rate. You get out past that 6-7 months and you get into the mature cow herd, less than 1% of those cows out there are shedding C. parvum, and the ones that are shedding are at a really low level, 1 to 100 per gram of feces. If we look at what's going on with E. coli, indicator E. coli, all the cows and calves, 100% of them are shedding, and they're all shedding at high rates, 100,000 to a million to 10 million, depending on what cows you look at. So we can already get a sense that there may not be, just at the end of the cow, be a good correlation. There's always the indicator, there's not always the pathogen of concern. So we won't find the correlation at the cow all year. We're probably not going to find it in water. So if you take a look at, remember that data from the Shubert Watershed here at Sierra, we found really high levels of E. coli in this case. Looked at over 600 stream samples between here and Hopland, 8 total rangeland watersheds over 2 years. Found trace C. parvum, 1 or 2, just detected in less than 5% of these 600 samples. So very little C. parvum leaving these watersheds basically at this scale right at the base of the grazing event, at the grazing bout. And so we're not finding a good correlation. The cows that were in this field were calving, they had the young calves, so we had the worst case scenario. These weren't dry cows that we wouldn't expect to be infected anyway. This was the calving herd, basically. And this facility is very infected. I think there's 60% infection at this facility. So we would have expected to see it here, if anywhere, but we didn't. If we go up into the mountains a little bit, into the Upper Feather River and Bridgeport Valley, we've been working with those grower groups quite a bit in the last several years, working on E. coli, fecal coliform exceedances. And basically we did an experiment over 2 years, 2007, 2008. They graze up there May through October when the snow's off. They irrigate. And so you've got a valley. You've got water flowing through it. And there's a couple streams coming in. They divert and irrigate. And then all the water exits the valley in one spot or in a couple spots. So we sample what's coming in. We sample what's coming off. These valleys that we looked at across the study, so there are about 5 or 6 valleys, range from 1,000 cows in the valley to upwards of 20,000 cows in the valley. 1,500 acres of irrigated, all the way up to 32,000. And basically, what we found was, break this down for you. If we look at indicator E. coli, if the sample was less than 235, or if the sample was greater than 235. So this is safe. Right? This is not safe. That's our current paradigm in terms of using indicator bacteria to monitor for human safety. So safe, not safe. We look at crypto. We had 8 total samples positive for crypto. 5 of those, 6% occurred when the water was safe. From the indicator bacteria perspective, 3 of them occurred when it was not safe. Salmonella, all positives. 9 of them occurred, 12%, when the water was supposed to be safe. 3 of them when it was not safe. Campylobacter, hey, didn't find any. That's good. Take that one off the list. It's expensive to test for. We're glad to not deal with it. E. coli 0157 had 6 samples positive. 4 occurred when E. coli was less than 235, and 2 occurred when it was greater than. I mean, you guys get this, right? I mean, this is important. This is not about livestock. This is not about any issues. This is about, we're saying the water's safe, and we're saying it's not safe, and there's a big discrepancy in what's going on out there, what we're observing. At the base of 20,000 cows. You have a question?
Yeah, the detecting levels that were not safe for those organisms?
Most of them were trace. We're working hard to find these pathogens, so 2 to 3 to 10 Cryptosporidium parvum. The E. coli is an amplification, so we take the water sample and we grow it, we culture it, we do everything we can to get that one E. coli, if it's there, to multiply. So this is an amplification method. And then these 2 are showing numbers of where there's a positive, this one, where there's a positive of less than 2 MPN, most probable number. So numbers that are probably below the infectious level, if we'd have to drink a lot of liters of water to get infected.
So in both cases, it is reasonable to say that there weren't infectious amounts of the organism?
That's what I would say. I would say, in terms of just yes, no, there's more commonly yes, below the standard. In all cases, unless your immune system's really compromised or you're an at-risk individual, you're probably okay to drink a liter or so of this water. Yes?
Or are you saying the indicator didn't indicate a whole lot?
Didn't indicate a whole lot. Yeah, so I'm just trying to make that clear, because there's a much bigger issue here as we all go about this process of regulating for E. coli, complying with E. coli. And this is perhaps novel to California. I had to drag epidemiologist to the table to study this, because he's like, we all know this. The drinking water industry, most of the environmental microbiologists already know that there's not a good correlation, and most of them are already monitoring for the pathogen, say at the intake of the treatment plant. But we need to have this information available for this landscape. And so we really need to think about what's happening. I'm not saying we shouldn't use these standards. I'm just saying we need to understand how they correlate to risk better before we go a whole lot further down the road to spending money to comply with them or regulate based upon them. And so then, I can't ever get away from this with a group of cattlemen. They want to know how many were above. Remember, this is above and below, and I just merged the two. Well, how many of those hits were above, Ken, and how many were below? And so across all these valleys, 8 positives for crypto, 5 were above. Now there's camping, there's ranchettes, there's Forest Service campgrounds, there's hikers. There are some cattle, perhaps up on Forest Service allotments. So there is activity in the watersheds above, but it's not that very intensive grazing and irrigation that we have below. So there were more above, but I wouldn't say that this is really a difference. Salmonella was consistently higher above than below. Again, no Campylobacter. E. coli 0157, consistently all the hits were below livestock, which also isn't that surprising given, remember, how many E. coli are in the feces of these cattle. There's a likelihood that that would be the pathogen that we would most often see relative to cattle, as opposed to some of these others. And so to kind of reconfirm that in a bigger scope, looking down, remember all the samples that were collected in the delta, and got this data from Rob, and basically out of 955 samples, if you look at again, below the standard for E. coli, above the standard, the mean concentration for E. coli for those samples that were below the standard was 22. The mean concentration for indicator E. coli for those samples that were above was 470. Take salmonella, the mean concentration when it was safe was 0.3. The mean concentration when it was not safe was 0.25. So basically the exact same kinds of results. Yes?
When you do say E. coli, is it determined whether that was a bovine source, human source?
No, we're not fingerprinting right now. We're just trying. We're at a step back from that. What does this indicator mean? If it means something, if it's indicating there are pathogens, then I would recommend fingerprinting E. coli. Right now, if I were going to fingerprint anything, I'd fingerprint salmonella, because that's what's going to make you sick, given that we don't see any correlation between these two. If you look at Shubert producing E. coli, the kind that'll make you sick, again, there's 2 types of cat classes. There's type 1, type 2, and basically had 2 in each class. Less than about 0.1% of all these samples had pathogenic. Now we're using pretty good methods with pretty low detection limits. So where are we at? We were hoping for that nice, good relationship. This is just from the Upper Feather River and Bridgeport. This is indicator E. coli. That's salmonella. Now the numbers are low, as I indicated, but I can't really find a pattern in there. No matter what statistical black magic I bring to bear, and I do that often, but still couldn't get it. So what could be going on is that down here in lower levels for indicator bacteria, we're not seeing the correlation. Get out here to higher levels of indicator bacteria and pathogens, we would suspect, this is a hypothesis, that this relationship would kick in as we might expect. This one always does that. So I'll see if I can remember what the bottom one is. But in summary, significant indicator bacteria associated with direct range and pasture runoff. Concentration increases with spatial reduction in concentration with increased spatial scale. Greatest at the pasture, lower at the watershed, even lowest at the delta. There's a significant influence of basically watershed hydrology and management on this. And just one more, maybe go forward one if you would. Okay, and then basically the last slide is we consistently find very low levels of pathogens in these waters that we're monitoring. That's the first good news. Unfortunately, we aren't finding a good correlation for when we do find those with these indicator bacteria. And what we are getting very strong hints of, and what we're going to talk about after break, are what are some of the management opportunities that exist for us to reduce microbial pollutants in general from these systems, because that should be a goal, regardless of what we have to do to figure out how to regulate this particular constituent. Yeah. So, questions?